Guys, so clearly I am absent again. Sorry, but I'm actually pretty sick today. What I'd like to do is just go through the notes as if I were there, in lieu of asking me questions, ask each other questions. We'll address any questions you can't address yourselves when I get back. But we're gonna try to push forward with the notes and push forward with the homeworks and things like that. So anyway, I believe we left off here. If not, feel free to fast forward. Draw a normal distribution and use the empirical rule to answer each question. So the mean test score of the Unit 1 assessment was 82. So my mean here is 82. With a standard deviation of 4. So my sigma equals 4, which means I'm going to be going up and down by 4. So let's go ahead and get those numbers in there. That gives me 86. This gives me 90. And if I make a mistake, excuse me, I am not the best right at the moment. Keep going there. 74 and 70. Okay. So 95% of scores were between what two scores? So 95, if you remember, corresponds to 2 standard deviations. And so that would be here, right? 1, 2, and here, 1, 2. So this is the area that they're referring to. And that would be the scores of 74 and 90. All right, the mean age at a concert is 38 years old. I immediately stop, write that down. Standard deviation is 5.5. Stop, write that down. All right, so that gives me what? And excuse me if I mess up. 43.5. That's 48. That's 49. Add another 5. That's 54.5. Whew, probably going to do a little much worse with subtraction. That's going to give me what? 33. So it's 32.5. Subtract another 5. It's 27. Well, anyway, it doesn't matter because they only asked us for 32 and 43. That's 1 standard deviation, and that corresponds with 68% of the data, if you remember from the empirical rule. So that's my answer, 68%. The empirical rule helps us really understand the normal distribution better. It's kind of like a stepping stone. It is kind of a dull tool. However, it does give us an easy understanding quickly. Let's go ahead. It's worth our time to inspect this normal distribution and the empirical rule a bit further. I find it helpful to memorize or at least understand, be able to construct what these slices are as far as their percentage of the whole distribution. So what percent lies here if this much here is 68%? Well, since it's symmetrical about the center, that's half, 34% and 34%. Now let's inspect it further. Let's keep going. Remember, between these two bounds, 2 standard deviations, I'm going to end up having 95%. Right? But I've already used 68%, haven't I? So if I just want to know what these slices are, I'm going to need to do some subtraction. And that's easy. 95 minus 68 gives me 27. And I have not 1 piece, but 2 pieces. So I have to divide that by 2. Which is kind of cheating, I guess. So anyway, divide that by 2, that's what, 13.5%? All right. Now that we've got that, now let's turn our attention to the outside there. These slices. Okay. So we can fill in what we know. This is 34. Whoop. I don't know why it's all fancy now. Okay, yeah, I'm on crayon. And we know this is 13.5 and 13.5. What are these slices on the outskirt? All right, sorry about that. My dog jumped on me and I had to pause recording. So I was talking about these pieces here, and from which I should subtract my existing percentage. So how much is this? Right, that is 95%. And how much is this? Excuse me. 99.7%, remember? That is 1, 2, 3 standard deviations away. And so, to find out what this slice is, what I must do is take 99.7 and subtract from that 95, and I'll get 4.7, and that's to be divvied up between the two. So 4.7 divided by 2 gives me, what, 2.35% on the tails. And yes, sometimes it is necessary to even speak about these out in yonder far land. Okay? How to get those numbers? Remember, the whole curve is 100. And I use 99.7, so that leaves me with 0.3 to be divvied up. So 0.3 divided by 2, this is not correct math, 0.15. So 0.15%. And now, I caution you, when you're working with these and these, when you turn these into decimals, I mean, it's easy enough to take 95 and turn it into a decimal. But it's sometimes not straightforward, or at least it's easy to misstep, I should say, when changing these. Remember, you have to move twice. You have to move twice. Okay, let's keep that in mind. All right, let's keep moving along. The mean test score on Unit 1 assessment was 82. Stop and write. What percent of test scores fell below a 74? Okay, let's fill out the x-axis until I get to where I need to go. So standard deviation was 4. So I'm going up to 86, 90, 94, 78, 74, and 70. I feel like I just did this. What percent fell below? 74. Well, sometimes it's easier to take what you know and subtract that from what you don't know, or from the whole. You know, do converses. There's lots of ways to do these problems, is what I'm trying to say. Well, let's think about how many standard deviations that is out. You know, what's this distance? That's 2 standard deviations, right? So how much is within 2? Oh, that's 95%, right? Or better yet, 0.95. So if that's 0.95, what is left over on the tails? Well, what's left over on the tails has to be 5% or 0.05, but between the two, so this has to be 2.5% or 0.0025. Make sense? Oh, that's for percent. What did I say? 2.5. Okay. What percent of test scores fell above 78? Right, where this scratch? Why are you writing pencil? Above 78. So they want to know this area. All right. What's the best way of doing this? Well, I would probably think about how much is within one standard deviation, since that's what my one boundary is. So I know that that's 68%, right? Which means how much is left over. That means that there's 32% to be divvied up between the tails here, and I only want one of them. So half of 32 for this area here is 16. And so if I wanted the total area, I'll simply just add the two. Pardon me. So that's what? 70, 85%, right? Wait, no, 84. I think the cold medicine's kicking in. All right. Let's keep trudging along a little bit here. Standardizing. What does that mean? Well, let's explain through an example. Mallory took a physics test and got 86%. The question is, how did she do? Remember, we only really care about how we're doing in comparison to others because we're comparative social animals, right? So if the class mean was 97%, did she do well? Well, if Mallory has an 86 and the mean is 97, is she above or below it? She's below it, so I would say no. She's below the mean. Or typically just say she's below average. If the class mean was 62%, did she do well? Well, she's 86. Is that above the mean? Yes. Considerably so. I'd say yes. She's considerably above the mean. The location of an observation in relationship with its mean is one that is often asked. So often, in fact, we have a method of calculating how far away an observation is from its mean. This method is called standardizing. And it is the process of counting how many standard deviations above or below the mean an observation falls. And that's really all it is. How many standard deviations above or below the mean of an observation is. In the physics test, Mallory scored an 86%, and on the next test, she scored 82, which was more impressive. Well, we would want to know how Mallory did relative to the class. We use standardizing to compare two things that have a different scale. On her first test, Mallory scored 86%, and the class mean was 83. Her second test, Mallory scored 82, and the class mean was 78. So either way, she's above the mean, which is great on Mallory. Way to go. But still, which one did she do better? We have the standard deviations here as well. So assuming that these scores are normally distributed, which isn't that unfair of an assumption. If you look at SAT scores, they invariably end up in almost a perfect bell curve. To me, that's one of the best indicators that we're dealing with some sort of biological variable. That's my greatest evidence for thinking that that's what that is. Anyway, oops. Let's standardize it. Subtracting her scores from each of the mean tells us the distance from the mean. But to determine if this distance is typical, we divide by the standard deviation to see how many standard deviations it is away from the mean. The resulting number is how many standard deviations away from the mean an observation is called the z-score. So let's underline that. I like to think of it as how many standard deviations fit in that distance. So here are the numbers for the first test. What is the distance between her and the mean? Well, we're going to look at her value minus the mean. In this case, it is going to be 86 minus 83, which gives me a distance of 4. Now that 4, we're going to see how many standard deviations fit in there. So I'm going to divide it by 4.5. This is going to give me something. Let me look it up. .67. And this is called the z-score. Now, I wouldn't want you to do it in pieces like I have done here. I was just kind of hoping that you would see that what we're really doing is seeing, how many standard deviations fit inside this distance of 4. When we do find the z value, we're going to want to go ahead and just do it in this approach all at once. So let's do that for the second test. So her second test, she had 82, and the mean was a 78, which still puts her 4 above, but the standard deviation was 5.2. Let's put that in a calculator. And we will get 0.77. So you tell me, on the normal curve, which one's further above the center? 0.77 or 0.67? Which one's further? So a z-score of 0.67 means that Mallory scored 0.67 standard deviations above the mean. A z-score of 0.77 means that Mallory scored 0.77 standard deviations above the mean. Clearly, she did better on her second exam. These are called z-scores. If an x is an observation from a distribution that has no mean and standard deviation, the z-score for x is the following. I think we just wrote it, but let's go ahead and write it again. It's fun to write. The z-score tells us how many standard deviations from the mean an observation falls and in what direction. Observations larger than the mean would end up with positive z-scores, and observations smaller than the mean end up with negative ones. do some examples. Female shoe sizes are approximately distributed with a mean of 8 and a standard deviation of 0.75. I like to write that down. Find and interpret the z-score for a female with a shoe size of 6. So that is what we call our X. So I like to write down every time I use an equation. I like to write it down in its pure form and then go ahead and substitute. And there you have it. So negative 2 over 0.75. Negative 2.2. So we'll go with that. So we should always include a brief summation of our findings in full sentences. What would we say here? Simply say a female with a shoe size of 6 is 2.67 standard deviations below the mean. All right, I'm going to do one more, then I want you guys to do the last one, and we'll call it there. Joe is 74 inches tall. The average height of an adult male is 70 inches. Okay, so I'm going to go ahead and start writing this stuff down. And standard deviation of 2.5. Find and interpret the z-score for Joe's height. Joe, what a fantastic name. Anyway, z is going to equal x minus mu over sigma. Let's go ahead and substitute. I got 3 pieces. That's what, 4. Okay, that was going to be not 2. That's 1.67. So, see above? Yes. How much? Joe is 1.67 standard deviations above the mean. Include context. Height of adult males. We'll have you guys do the third one, compare your answers, and then we'll come up with a solution together. Hopefully the next day we'll go ahead and look at how you did. And let's have you do... I'm looking at the practice set here. I'm thinking the first page of the practice set. Okay? So number 3 and the first half of the first page of the practice set. All right. See you guys next day.